Welcome back, Math Models for the Social Sciences students. Today we're going to talk about chapters 3.5 and 4.1, Systems of Equations, and then Exponential Growth and Decay. Today is actually March 31st, 2022. This lesson was supposed to happen on Monday, the 28th, as you could see there, but we had to cancel class. So here we are doing it today during our Zoom lesson. This lecture will be recorded and posted in eCampus in our module folder. So first, I'd like to talk to you guys a little bit about where we are in the course. Like I had mentioned, we had a little bit of a slip up this particular week. And in here, you'll notice we have this week is a little bit off. Basically, we're doing this today, 3.5 and 4.1. Oh, no, I'm sorry. That's the week from last week. This week is a little bit off. This week on Monday, we were supposed to do today's lecture, and now was supposed to be our web assign time. So instead, what we're going to do is we're going to change this, and we're going to make it that the web assign that was supposed to be due on Sunday, April 3rd, is going to be due on Sunday, April the 10th. And that way you have more time because it is Thursday, and I would like to give you sufficient time to do the work associated with today's lesson. So it's not due this Sunday, it's due next Sunday. And then when we get together on Monday next week, as you can see here, I'll change color. When we get together on Monday of next week, you'll see that we're focusing on chapters 4.2 and 4.3. So between now and Monday, I'll ask that you make sure you read through and outline chapters 4.2 and 4.3 so that you know where we are when we get together and talk. And on Monday, I do plan on staying after a little while if there's anyone who'd like to come and talk to me or discuss anything or go through any questions. On Thursday, that next week, a week from today, we'll do web assign practice for both of them as needed. Okay. The following week, as you can see, is going to be a little bit lighter. There's not nearly as much as there was. Here we only have chapter 4.4 and then a little bit of exam prep. And then again, the following week, we're going to have our exam. So we're just about turning the corner here and finishing up the end of the semester. We have only 5 sections left that we will be studying. And today we're going to do 2 of those 5, which is chapters 3.5 and 4.1. So let's begin now. Let's talk about systems of equations. You probably recall when you were in high school in Algebra 1 in the 9th grade, or possibly in Geometry and Algebra 2, focusing on the concept of systems of equations. That is when you have 2 or more equations with 2 or more variables, such that you should be able to find out what values of those variables will make all of the equations of the system true. What is a system of equations? Well, it is a group of 2 or more equations containing 2 or more variables. To solve the system means to find the values for its variables. This course will focus on 2 methods for systems, graphical and algebraic. So we'll do both of them. We're going to walk through how to do algebraic systems. I'll show you the details of it. It'll just be something of a reminder from your high school years. But we'll see, really, it's a lot more practical to lean on graphing utility Desmos and to think about technology. Comes out much quicker. And remember, we're here in Math Models because we're learning about how to apply mathematical principles. We're not here to really learn math as much as we are to use technology and understand enough math to be able to answer specific kinds of questions. All right, so let's take a look at an example out of our textbook. This is a question about coarse gravel and fine gravel. To show the method, we look at a simple example. We have $900 to spend on the repair of a gravel drive. We want to make the repairs using a mix of coarse gravel priced at $28 per ton and fine gravel priced at $32 per ton. To make a good driving surface, we need 3 times as much fine gravel as coarse gravel. So how much of each will our budget allow us to buy? This is a typical SAT question. You probably saw this if you were studying to get to pass one of the standardized tests like the PARCC or the HESPA or the GEPA. These are the kinds of questions that they make many different versions of it. You might have seen something like this having to do with nuts, like there are 5 pounds of cashews and 3 pounds of peanuts, and you have $50 at the store, they would give you a relation like there's 3 times as many cashews as peanuts or something, and then they'll tell you that The peanuts are $6 a pound and such, and carry on the same way. I've also seen this done with saltwater solutions and alcohol solutions where there's a percentage of the solution, and we can also relate it in that way as well. This is a typical question. This is just one of many different models of that kind of question. So how would you do a question like this? Here's how you would go about it. First, let's identify some important variables. I'm going to let C equal the amount of coarse gravel in tons, and F can be the amount of fine gravel in tons. I think it's kind of a good idea also to include that label. This is a measurement of tons of something, not dollars, but tons. And when you write that down in your let statements or your definition statements, it does kind of help a little bit to remember which variable is what kind of quantity. So let's come up with a model. The model is a written expression that's really explicit and simple to understand. And it does make me believe that I know it's $28 for the coarse gravel. So I think at $28 times the tons of coarse gravel plus, and then $32 times the tons of fine, and then that ought to equal 900 if I add it up. So that's my first concept, is thinking about what it looks like at the cash register when I'm buying all this gravel. The other thing is the relationship between the two quantities of gravel. We are told that we need 3 times as much fine gravel as coarse gravel. So we're going to say the total fine gravel equals 3 times the total tons of coarse gravel. Now, you could take those two models and rewrite them now a little bit more simplified so that they look like equations using variables. It'd be something like this. And then what I would encourage you to do is take this information and run with it over there on Desmos. What I would do is modify, put in different variables for C and F. I like to use X and Y. And then you'll get 2 lines and you just want to see where they cross. Now, if you did this with algebra, the fact that it says F equals 3C kind of gives you license to rewrite the top equation, but insert 3C in there where F is, and then you'll have an equation all in one variable C. And then after you find C, you go back and find F. That's called substitution. So this is solving an system of equations by substitution. If you want, you can do it that way as well with a pencil and paper. Either way you do it, you'll still get the correct solution. So let's take a look now at what it would be like if we tried to solve this equation. So there's your system. And here's the arithmetic associated with using substitution to answer this solution. We see that we first took the top equation and carefully solved it for F. And we have a little bit of an ugly expression there, 900 minus 28C over 32, but it still is a valid, appropriate expression for F. And notice that the second equation says F equals 3C. So if F equals 3C, then that expression equals 3C. And now you have an equation that's all entirely in C that you can solve. I'm sorry, let's come back. That you can solve. And when you're done, you'll get what C is. Whatever C is, 3 times it is going to give you F. So what you're looking at here, friends, is solving a system by substitution. Let's take a look at key idea number 3.7. How to solve a system of 2 equations and 2 unknowns. Solve both equations for one of the variables. And then the solution of the system of equations is the intersection point of the 2 graphs. This is found by using the Croft-Grass method. Now, the good news is you don't have to solve both equations for one of the variables because you're using Desmos. If you were using a TI-86 calculator or any kind of graphing calculator, it wouldn't give you the opportunity to enter an equation that has 2 variables. It would only say y equals, and then you'd have to put in whatever the answer was after your equation solved it for y. In Desmos, you don't have to solve it for y. You could go right into Desmos and put in the 2 equations just the way you see them in the very first rectangle over there, unsolved. And you'll still get 2 lines and they will cross somewhere and you will be able to solve your system. So now let's take those 2 equations and let's apply them to the concept of graphical analysis using Desmos. First, what we would do is we would go on in and enter the 2 equations like you see here. Okay, so I don't know what happened there, a little technology issue there. Anyway, so you put the 2 equations in. Notice I changed the F into the Y and the C into the 6. I'm sorry, the C into the X. You did not have to solve it. You could have put it in just the way it was up front without being solved. Either way, they'll cross. They're two lines, they cross. Zoom in and out, play around with the wrench a little bit. And before you know it, you'll find the place where they cross. 7.258 is the answer for F. I'm sorry, is the answer for C. And 21.774 is going to be your answer for F. Okay, so you should be able to use Desmos to do it. I'd like to show you now, friends, how to open up Desmos and actually do it. Okay, we're going to look at Desmos.com right now. And we're going to go into Desmos, and we're going to ask Desmos to show us graphs for these two important functions. The first function, if you recall, take a look over here again. It's going to be 38C plus 32F equals 900. That's like 28X plus 32Y. The other one is y equals 3x. Okay, so at a first glance, as you can see, I do not see where they cross. So I will zoom out. And then I'll just kind of click in the area, hover over it. You can click it and it'll stay. And there's your solution. So we should be able to solve virtually any system of equations at this point, because you're able to see where they cross, and where they cross is, of course, the solution. Okay, now you could do it with substitution or elimination, but from here on in, guys, please start applying the ideas in Desmos to get your answers. I want it to be easy for you. All right. And then you could make a sentence up. We should buy 7.26 tons of coarse gravel and 21.77. Of course, you can make a sentence out of it. All right, so that's the concept of system of equations. Let's look now at example 3.9. It's about a picnic. We have $56 to spend on pizzas and drinks for a picnic. Pizzas cost $12 each, and drinks cost 50 cents each. So 4 times as many drinks as pizzas are needed. How many pizzas and how many drinks will our budget allow us to buy? So this is just like the story with the gravel. We have a limit. The limit is not $900 for gravel, it's $56 for the restaurant. And we have two different things going on. It's not fine and coarse gravel, it's pizzas and sodas. And on top of it, we have a relationship between what we expect for the pizza and the soda to be 4 times as many drinks as pizzas are supposed to be there. So we can make two relations. The first relation has to do with the amount of money being spent and how it should be $56. And then the next important thing is supposed to be a relationship between the pizzas and the drinks, something like this. And as you can see, we have some nice models written here. I encourage you to write the models out. Well, when you take WebAssign, when you do your WebAssign homework, they will have little boxes for you to enter things and create models like this. It does make sense to consider that 12 times the pizzas plus 50 cents times the drinks is the cost of the picnic. And then on top of that, we have the number of drinks must be 4 times the number of pizzas. So if you use some variables here, like capital P for pizza and capital D for drink, then these little models turn into these little equations here. And you can go right into Desmos and make Y, D, and make the P into the X, and you have nice equations, and you can solve. Here, for your textbook, they're assuming you're using a graphing calculator, which is why they keep on insisting on solving for D. And you don't have to do it that way because you have Desmos. You could just go right in with 12x plus 0.5, y equals 56, and y equals 4x. So now that we talked about how you do it with Desmos, let's talk about how you do it with an algebraic equation. This is how you would solve a system of 2 equations algebraically. First, solve one of the equations for one of the variables. Second, put the expression you got in step 1 into the other equation. And then for step 3, solve the linear equation in one variable, and last, get the other variable by going back. Looking a little bit like this, since D equals 4P, I guess that gives me license to insert in the position of the D this expression 4P. And now I have, as you can see here, an entire expression all solely in one variable, p. So that's something you can focus on without worrying about graphing or systems at all. That's just an old topic, how to solve a linear equation. Once you're done solving it and you get your answer, next, what you should do is come back to the original equation, which is right here, and put that answer 4 in there to get your final solution. As you can see, p equals 4, so then I guess d equals 16. Okay, so solving the equations is really a cinch when it comes to using Desmos. If you have a graphing utility, you don't have to worry too hard about solving systems of equations. It kind of just balances out perfectly that way. If you were going to do it to the Desmos, it would look like this. They would cross there and you get 416. So again, I encourage you to give that a shot and walk through that and experience using Desmos to get your solutions. All right, so now let's begin chapter 4. In chapter 4, this is chapter 4.1 lecture, we're going to learn about exponential functions. What is an exponent? An exponent is a number that you are raising a power to. It's the little number you see raised up at a smaller font size. An exponential function has a model that has a base that changes by constant multiples of itself. There are two population analyses that change naturally according to a model of an exponential function, and that is growth and decay. So if you see a population booming because of people being born and the population is thriving, that's exponential growth. When you see decay or matter disintegrating, or if you see rot or something like that, where things are literally decreasing, like a flower that is dying, things like that. That's where you see exponential decay, where in the same way that growth has a fancy curve to it, decay has a funny, interesting curve to it as well. And they are ultimately, of course, inverses. In our situation, it's actually pretty straightforward because the only real application is knowledge of exponents. And so it does become actually a little bit of a more basic topic than you'd think. Let's take a look at n equals pat. I want you to remember pat because those are the important elements of an exponential function. P is a multiplier, A is some number, and T is the actual variable. T will be the variable. So this might be 2 times 6 to the T, or it might be 1/2 times 1/5 to the power T, and the power that is T is going only to the 1/5 or only to the thing directly next to it. Remember, the T does not apply to the P and A, it only applies to the A. If I put parentheses around P and A, then that would be the case, but it's not. Okay, so this is the general idea of growth. It's n equals pat. Let's pretend for a minute in this beautiful petri dish here that I have 3,000 bacteria. And I can find that out by using an estimation, and microbiologists have a way to estimate large numbers of, for example, bacteria. But what's happening is this particular strain of bacteria, this particular species of bacteria, they happen to double every minute, or they double every hour, or they double every 6 seconds or something like that. But every period of time that goes by, it doubles and doubles again and doubles again. You may recall when you were studying biology that the way that cells reproduces is through splitting, So fission is when it sounds like division, but it's fission with an F. It means that it's a cell that just splits in half, and now there are 2 cells. So if you have 3,000 cells and all 3,000 of them all cut in half, then suddenly your petri dish will have 6,000 cells. And if you do it again and split, it becomes 12,000, and then it becomes 24,000. Notice that the basic mathematical principle is that you're just timesing by 2 again and again and again. And as you can see, every time you multiply by 2, you're really, by leaps and bounds, really increasing. Before you know it, you'll be in the 100,000s and millions and even tens of millions and so on. Exponential functions really escalate quickly. Instead of linear functions, which have a constant, steady, predictable increase, exponential growth is sudden and strong. So you might have heard the expression in our English language, something is growing exponentially, or something is exponentially impossible, or exponentially challenging. That means really extremely. Exponential is a synonym for extreme. And it's because, as you can see, we don't go 3,000, 6,000, 9,000, 12,000, 15,000, and we go 3, 6, 12,000, 24, 48,000, 96, it just carries on, it gets really huge, really fast. So I just want you to remember that's why, the exponential growth works that way. And here's something that's kind of interesting. If you take this concept of this bacteria and you consider what the answers are, and then you try to apply some kind of clever model, you'll happen to notice that it does follow perfectly the concept of an exponential count. Here, if we start with 3,000, 3,000 being our initial value, meaning it is at time 0, the very first amount that we've counted before anything or any time has passed or anything has happened. 3,000 can be expressed as 3,000 times something to the 0. I want you to focus on this with me for a minute, friends, okay? 2 to the 0 equals 1. Anything to the 0 equals 1, and that is any number, any algebraic expression. 500 billion to the 0 is 1. 0 to the 0 is 1. Everything to the 0 is 1. So that be the case, why not apply that concept to represent the first term being unchanged? 3,000 times 1 will give you 3,000. In other words, for all of the exponents, whether it's 2, 5, 10, if you start counting all the exponents, the first one is always 1. 1, 2, 4, 8. Or how about we multiply by 5? 1, 5, 25, 65. Or what if you multiply by 10? 1, 10, 100, 1,000. In other words, in counting exponents, we always start with 1. So if you're going to start with something else like 3,000, make it that it's 3,000 times whatever the base is to the 0. In other words, like it's times by 1, so that it remains what it was. Notice that now what's happening is I have exponents increasing and increasing again and again and again. That's because when you multiply it by 2, and then by 2 by 2, and then by 2 by 2 by 2, it's ultimately just by another exponent again. So if you can remember this concept or grasp this concept, then what happens is n equals pat does kind of make sense. The p or the first order principle, or whatever the first thing was, p, the initial value, is 3,000. A is the base or the multiplier. Notice in this situation, you're multiplying by 2 over and over and over again. So 2 is the A. And last but not least, t is our independent variable. So now I'd like for you guys to take a close look right here at this part. I don't know if I like that color. I don't know if you can see it. Let's make it green. There we go. Okay, and you'll see that the p has been inserted as the initial value. I need you to remember that, guys, okay? So if you see a list of numbers and it's exponential, whatever that first number you saw there, this time it's 3,000, that's the p. Then what are you multiplying by over and over again? 2, right? So that means that 2 is the value of a. And then just set up this, construct the function. It's n equals pat. Maybe for us, it's going to be y equals pax, but it depends as usual with how WebAssign decides to play around with letters and variables. It's up to you. It's up to them how our variables will turn out. Okay, so this is the explanation and the concrete reasoning of why the formula is n equals pat, and it does follow the a concept of something doubling or tripling or 5 timesing over and over again. All right. Great. So carrying on with the Petri dish, let's take a look at what it would be like if instead of it being a growth, meaning that they're splitting, that they're dying. Maybe they're dying because there's something in the liquid, or there's or because it's just natural old age. It's time for them to pass, or whatever that is. But in other words, if instead of it being that it's doubling, let's pretend it's being cut in half. So we have 3,000 bacteria, and then at the end of the first hour, half of them are gone. Then at the end of the next hour, half again of what was left was gone. And then again, we'll take half again and again and again. Can you see that we wind up taking a half of a half of a half of a half like that? And there's something of a Russian doll effect where you have the one leads to the other in an infinite way, and you could just carry on and carry on. Ultimately, it does feel like you'll never really quite get to 0 if you do it arithmetic this way. But nature does tell us that we can eventually completely smite out something in this situation, like a bacteria or a contagion or some kind of foreign object that way. So The exponential decay happens in the same way growth happens, but as you notice, the value of A, our base, is not a number that's a multiplier, it's a fraction that feels like it's shrinking it. In fact, every number that is greater than 1 is going to be exponential growth. Any number for A that is less than 1, like 1/2, represents decay. And that's because when you multiply something by anything bigger than 1, it enlarges the number. If you multiply something by a fraction less than 1, it will shrink the number. So that's the connection. Values of A, or the base, that are greater than 1 represent exponential growth. And then if it's less than 1, it's decay. So here we have cases of using 3,000 with a decay factor of 1/3. So let's go through what would happen. Don't you expect it to be 3,000 and then 1,500 and then 750 and then 375 and so on and so forth? You can get those numbers with this arithmetic. First, if the first one is 3,000, let's call the exponent 0 so that 3,000 comes out and it doesn't matter what my base is. But at our number 1, I'm multiplying it by 1/2. At our number 2, the thing that was multiplied by 1/2 is getting multiplied again by 1/2, which makes it look like 1/2 squared. Then we'll take that same thing and multiply it by 1/2 again and get the cubed, and so on and get the 4th. So decay and growth are really the same thing in terms of the pattern of how the function comes out. But remember, growth is growing and enlarging and increasing, whereas decay is shrinking and becoming smaller and smaller. All right. So if you look at this situation, you should be able to recognize that right here we have A, right here we have P, and you should be able to come up with this statement here. Right. You will see questions like that in WebAssign where there's a story about bacteria or about something that is increasing or shrinking. So I want you to take a look now at these two functions. In the first one, we're talking about bacteria that are doubling every hour. In the second one, we're talking about bacteria that are being cut in half every hour. And I want you to look at the idea of the bases. In the first one, the base is 2. In the second one, the base is 1/2. So if that be the case, notice 2 and 1/2 are perfect reciprocals. Now I want you to look at the two graphs that are being made from it. Don't they look like they're just about the same but backwards? In fact, if you take one and spin it, you should get the other one. This is the idea. And I want you to remember also that as you travel along the X in this direction, what's happening is your Y is increasing. But whereas if you travel along the X in this direction, same direction for this one, the value of Y is actually decreasing. Look at that, it's decreasing. And as time goes on, your population is decreasing, that's decay. As time goes on, your population is increasing, that's growth. So these are the functions that are associated with it. And they're both examples of exponential functions, but you should know, looking at a function, whether the base is larger than 1 or smaller than 1, because larger than 1 has a feeling of going up, whereas less than 1 is going to be going down, like we see there. Okay. So let's kind of summarize now exponential growth and decay by talking about exponential functions. This is key idea number 4.1. In this function, it's a function like this is exponential with a base of A if n changes in constant multiples of A. In other words, if t is increased by 1, the new value of n is found by multiplying again A. The formula for an exponential function is n equals pat, like I showed you. And for numbers 2 and 3, and this is important, if your if your base is larger than 1, then it's growth, and it will be showing an increase. If your base is less than 1, like a fraction, or the dreaded 0.99, which is used often in math models, then you are expecting it to be a decay and it will be shrinking. It's important that we're comfortable with that idea. Let's do an example of it now. Here, we're talking about radioactive decay, which is a common topic in chemistry class. Radioactive substances decay over time, and the rate of decay depends on the element. If, for example, there are g grams of tritium, which is a radioactive form of hydrogen, in a container, then as a result of radioactive decay, 1 year later, there will be this many grams of tritium left. Suppose we begin with 50 grams of tritium. Now, what's happening is use a formula to express the number of grams left after T years. In this situation, can you tell that the initial value is right here? It's 50 grams. Can you tell that the base is 0.945? Get used to it being an uncomfortable quantity. It's not always going to be 1/2 and 2. It's usually going to be 0.945, something a little bit ugly that way. So I would write, if we're going to say G grams in T years, I would make it G equals 50, which is our initial value, times 0.945, which is our base, to the power of T, something like this. If it helps, you could write out the actual model, which is the words as you see, but this is what we're expecting. Here in math models, we allow you to use the cross sign or the times sign. You could have done this also if you wanted to with parentheses or with a dot. All right. For part 2, it says how much tritium is left after 5 years. Remember what your variables represent. T is the number of years. So I guess what I would do is put 5 into the position of T and see what we get. Not hard to do, old school arithmetic. You could do that with a calculator, or you could do that with Desmos if you open a table, and you guys know that. Next, it says plot the graph of this over the first 30 years. Describe in words the amount of tritium that is present and how it changes over time. So if you were going to do that, all you'd have to do is put right in there y equals 50 times 0.945t to the t, but this time to the x, of course, and you get a graph looking like this. Obviously, it is decreasing. How long will it take for half of the tritium to decay? We would think about how much is half. Half of the tritium is 25 grams. I'm going to make a note of that. Half in other words, at what point will y equal 25? Best way to do that is to just go right in and type in the equation y equals 25 and see what happens on the graph. So we're going to add a new form. How long will it take for half of it to decay? We want to know what will happen when there's 25 left. So what we're doing is we're solving for 25. So make a new line, y equals 25. And when you do that, this is what it looks like on the graph. There's a line right there. That's obviously the y equals 25 line. It's that red line, and it intersects somewhere. And you can see right there that half of it will be left specifically at 12.253 years, or whatever the t stands for, hours, or whatever it stands for, 12.253 of them. It's years. Okay, so can we remember if they ask you how long does it take for half of it to be left? To take the amount that was given 50 and cut it in half, I guess you mean that 25 then. And then you can just plot that right onto the graph. Let's come back to this slide and try to remember how we did it here. That we included the original function, the original exponential function, and then we put in a cutoff, y equals 25, to see where it would cross. That is the quickest and easiest way to solve an equation when you're substituting a number in for y and trying to get x. All right, let's try another example also about population growth, also about exponential growth. In 1900, the world population was at about 1.6 million. On average, to find next year's population, we multiply this year's population by 1.014. Notice that's larger than 1 slightly, but that does imply that we're doing growth and not decay. And I do believe that the world is growing. The population is not decaying, it is growing. Now, part 1 says, explain why these assumptions tell us that the world population is an exponential function of time. Well, that's because, as you can see, on average, to find the next year's population, you multiply this year's population by the same number. So it's the same multiplication over and over again. And that's the reason why we would say it certainly is exponential. Here's what your book explains. The world population is exponential because our assumptions tell us the population changes by constant multiples. All right, next, so part 2. Find the formula that gives the world population W in billions as an exponential function of t, the time in years since 1900. Okay, so the way we're going to do this is we're going to say, okay, first of all, in 1900, what was the initial value? It was 1.6. Notice it says in billions. So I don't have to write out 1,600,000,000. I don't have to write it out. I'm going to say the word billion when I'm done, and I'm just going to use 1.6 then. Also, what is the base? 1.014. So I'm thinking it should be something like y equals 1.6 times 1.014 to the x, or in this case, we're using w and t. So it should look something like this. W equals all that to the t instead of x and y. Also, we have a model there for you that if you wanted to write it in words, it would look like that. For part 3, it says make a graph of this world population from 1900 to 2010. That means go from 0 to 110 because remember, this is years since 1900. So I would go into Desmos for that. Take a look at how we do it in Desmos. Start by entering the actual formula. Remember to switch around x and y, and then get yourself a nice graph of it. You'll notice it really doesn't go up above 10 billion. So why not make the y-axis go from like maybe -10 to -20 to +20 or something, a little bit of a better image. And now it says, according to this model, when did the world population reach 5 billion? Just like before, when was it cut in half? You know, and you did y equals 25. Here, you're going to need to do y equals 5. So we'll type in y equals 5. And then we'll look at where that line is. And where do they intersect? Apparently, the answer is 81.957, which means 1981 at the very end of the year 1981. So this was a little bit of a shorter lesson than average. I think, you know, we are still here until 2:35. I'm going to dismiss now. I've taken attendance using our participants list, and we're going to stop our recording and open the floor to questions. Friends, I really do appreciate your close attention to my lesson. The next web assignment is available for you to do. And when we get together on Monday next week, if anyone has any questions, we can answer them at that point. I'm going to stop the share now, and then we're going to ask for anybody for questions and dismiss. Once again, thanks so much and have a beautiful night.